Let me go ahead and test my sound. Do I hear myself? I can hear myself. Do I see my hand moving in front of the paper? That all looks good too. Okay, let's get started. So today we are resuming with where we left off last time with the Unit 1 motion in one dimension topic. The plan for today is to derive the equations of kinematics and then start using them, and we're probably just going to do a bunch of problems after that. So without further ado, let's get started. Last time we talked about acceleration. Hold on, let me check. Do I have? Yeah, last time we talked about this. We introduced the concept of average acceleration. We defined it as the change in velocity over change in time. Pretty much the same pattern as the definition of average velocity being the change in position over change in time. And average velocity is, pretty easy to calculate once you know the first and last velocity that you're working with and the amount of time that passed between when you started and when you changed to the other velocity. But an even more convenient concept is constant acceleration, when the acceleration is a fixed amount and your velocity changes by the same amount every second, whether that's an increase or a decrease. And we talked a little bit about the whole moving man simulation, and we talked about the difference between increase in velocity versus increase in speed, and decrease in velocity versus decrease in speed. And we saw that through the simulation, we saw that an object will increase its speed only when the direction of its velocity is the same as the direction of its acceleration, and when the acceleration and velocity have opposite directions, the object will slow down, eventually come to a stop, and then turn around and then start speeding up, if it's in motion long enough for all three of those phases to happen anyway. So today we are looking at constant acceleration, and we are going to derive the equations of kinematics, sometimes called the equations of constant acceleration, or ECAs, and also sometimes called the uniformly accelerated motion equations, UAM. You might hear all three of those different names for those equations, and I think some people also call them Newton's equations of motion. So whatever term your teacher uses, it should all be referring to the same thing. So let's start off with a graph. And actually, I need to go ahead and unplug this headset because I already did my sound check. And I don't want my ears to be hurting later. And I might as well grab this ruler. And let's go ahead and draw ourselves a graph that shows us what constant acceleration looks like. Okay, so let's say that you have an object that starts at, this is going to be a velocity versus time graph, by the way, velocity versus time. And let's say this describes an object that's moving strictly in the x direction. Let's say that we're talking about an object that's just moving horizontally. It starts at this velocity, which I will call v initial, and it climbs up to some other velocity. I will call it v final. Maybe I should draw some dotted lines here. Did that work? Yeah, that worked nicely. And of course, it starts at some time, which I will call t initial. We could also just call it 0, but t initial over there. And by the time t final, let's say it's over here, by the time t final, it reaches a velocity of v final. If the acceleration is constant, that just means that, let me draw another dotted line here, that just means that the velocity increases over time in a straight line. Let me do this in another color. I'll go with orange. Okay, that's about right. So that's what that graph would look like. Constant acceleration on a graph is always a straight line. It could be going up or it could be going down. If the acceleration is negative, it doesn't really matter which direction it's going as long as it's straight. That tells you that the acceleration is constant. That is, if I were to, I don't know, divide this into, I don't even know how many subintervals I want to cut it into. A constant acceleration just means that if I take equal-sized steps in time, I get equal-sized changes in velocity for them. So the amount of velocity change from this time to this time, which should be that much over there, this amount, is the same as the change in velocity, if I drew these right, would be the same as the change in velocity, say, from this time to this time. So if I were to draw this and this, if I drew it correctly, then this over here, this gap in velocities should be the same size as this gap. That's what constant acceleration means. Okay, so what can we do with this? What can we get from this graph? First of all, we can calculate what the constant acceleration is in kind of the same way that we calculated the velocity on a position versus time graph last time. Was it last time or was it the time before last? I want to say it was last time. So we can just take the slope. On a velocity versus time graph, slope is going to give us our acceleration. Specifically, it'll give us the instantaneous acceleration if it's a curved graph. And if it's a straight line graph, then it will give us just the overall acceleration. It'll just give us the actual value of the constant acceleration. So if the graph was more curved, I guess I can draw something like that. Let me draw another velocity versus time graph here. And let's say this one is more roller coaster shaped. Maybe it goes around like this, up and down, and twirls around, and yeah, something like that. If I were to pick a particular point here, let's say I pick this point, then I can just draw a tangent line to that point. A line that just barely grazes that point on the curve. And if I were to calculate the slope of that line, that would be the acceleration at that moment, and then at a different moment, like say over here, we would have a different acceleration. This one looks like a negative acceleration, which makes sense because at this point, the graph is curving downward. Over here, the acceleration would be just a flat 0 for a brief moment, and so on and so forth. And over here, no matter which point you pick, the tangent line to a line is always just going to be completely parallel to that line. So all the points have the same instantaneous acceleration. That is indicative of a constant acceleration. So slope gives you acceleration. It gives you average acceleration if you calculate it between 2 points, and it gives you instantaneous acceleration if you're just trying to calculate it as the slope of the tangent line at 1 point. If I were to pick 2 points now, if I were to pick this point and this point and draw a line connecting them, then the slope of this line, this is what we call a secant line, in case I didn't mention that last time we did this. The slope of that secant line would give you the average acceleration between these 2 points. And as we can see, the actual accelerations between these 2 points were sometimes above the average. If I pick this point, you can see the instantaneous acceleration was a much steeper slope. And if I were to pick this point, you can see it was actually a negative slope. And if you combine all of that together, overall, the slope of this secant line gives you some sort of average for that interval. So now let me gather my thoughts and figure out where I wanted to go with this. I kind of lost my train of thought in all this. So slope gives us acceleration, whether instantaneous, constant, or average. And area is going to be something that's useful to us. Area is actually going to help us derive some of our equations. But before I talk about area, let's actually derive our first equation of kinematics. I don't think you'll be surprised that it's just going to be a rearrangement of the equation we saw last time. So over here we've got v initial again, and over here we are at v final. And I want to refer to this gap over here. I want to refer to this gap. I want to call this v final minus v initial. That will be relevant for later. What I can say, well, I guess it's going to be immediately relevant. If I wanted to calculate the slope of this line, if I wanted to calculate the average acceleration, which is also the instantaneous acceleration, which is also the constant acceleration in this special case, then all I would have to do is say that this acceleration, I don't need the average symbol on it anymore because it's a constant acceleration here, is equal to change in velocity, which is v final minus v initial, over change in time, which is t final minus t initial, just your typical slope formula between 2 points. Now, t initial is often going to be 0, so I could just call this t final, which I would more generically refer to as t. I can rewrite this as acceleration equals v final minus v initial over t final, which I'm just going to call t from now on. T initial we have eliminated because it's just equal to 0. If I rearrange this a little bit, if I multiply the t by the a, if I multiply the t over, then I get a times t equals v final minus v initial. And if I add v initial to both sides, then I will end up with v initial plus at equals v final. I prefer to write it the other way around, with v final on the left-hand side and everything else on the right, so I prefer to write it like this. And this is our first equation of kinematics. V final equals V initial plus AT. This only works if the acceleration is constant, or if the problem tells you to just treat the object as having an acceleration that is constant, and usually they'll tell you to use the average acceleration in those scenarios and pretend that it's a constant acceleration. So yeah, this will be your first equation of constant acceleration. By the way, your teachers might use different notation. Some teachers might say V is equal to V0 or V initial plus AT. That also works. Some people like to write V1 equals V0 plus AT, and some even like to do V2 equals V1 plus AT. That's all fine as long as you remember the previous velocity plus the acceleration times the amount of time gives you the new velocity after that amount of time has passed. As long as you remember this is the previous velocity and this is the velocity you end up with after some amount of time passes at some acceleration. By the way, I expect you to memorize this. I don't care if the AP exam gives you a formula sheet. I don't care if your teacher gives you a formula sheet. This is something you ought to remember because you use it a lot, and having it in your head is more valuable than having it on a formula sheet. What happens when you have a formula sheet is that you end up flipping back and forth between your test booklet and the formula sheet, and even though it might seem harmless, it's only a couple seconds, there are two problems with this. Problem one, the amount of time that it takes flipping back and forth between your formula sheet and your test booklet adds up over time, and you don't want that. It'll just make you even more anxious about how much time you have left. And two, if you don't know your equations ahead of time and you just take it for granted that the formula sheet will tell you everything, you're going to be in trouble because there are a lot of equations in physics that are going to involve these concepts. The concept of acceleration shows up in more than just kinematics. We're going to see it in the force chapter, for example. So if you are faced with a problem that mentions acceleration and you go to your formula sheet, you're going to be confused as to which equation to use that involves acceleration. And you really need to get to know your equations. And also, it's just easier to figure out what to do as you're reading the problem if you already have the equations in your head. I understand the whole anti-memorization sentiment that teachers have. I get it. But it's a bit overboard. I don't think memorization is inherently evil. It depends on why you're memorizing. I would say I'm against rote memorization, but not against memorization in general. There are advantages to just having things in your head and not having to look them up. And also there are some tricks that you can use to remember these equations. For example, for this one, I've got the F-I-A-T. I remember this as Fiat, like the car brand, or I guess for those of you doing AP Econ, you might remember the concept of fiat currency. So that's a little trick that you can use to remember it. But the most important thing, I would argue, is just look at the equation and try to understand it. Really convince yourself that it makes sense. Velocity after some amount of time has passed equals whatever velocity you started with plus, let's see, your acceleration times your time. Well, your acceleration is how fast your velocity changes, and your time is how long your velocity is changing. So that makes sense to me that the more acceleration you have and the more time you spend at that acceleration, the more you need to add or subtract from your starting velocity to figure out what velocity you end with. If you do that, if you just really try to make sense of everything that goes into an equation and convince yourself that it makes sense, the memorization becomes easier. And that's really what you should be doing. So when I say memorize, I don't just mean rote memorize. I mean really understand the equation and get to a point where you can kind of just reconstruct it on the spot and tell yourself, yeah, this makes sense. Anyway, my rant about memorization aside, let's continue with this graph. So we've got our first equation of kinematics here. We've got our, oh my goodness, why are my pens acting up today? We've got our first equation of kinematics over here. And now we need to get a second one. So our second equation of kinematics involves displacement. As you know, an object that moves at a certain velocity achieves a certain displacement, but also if it's accelerating, that will affect its displacement. If its velocity is changing over time, then the displacement will be affected in some way. So let's compare a constant, I guess this is a positive acceleration, to another scenario where you have a zero acceleration, which is also technically constant. So let's say I draw a graph over here with, let me move these out of the way. And I'm just now remembering I forgot to pick up my other books from the room outside. I'll have to remember to do that later when we do problems. I don't know why I'm remembering that now, of all times. But anyway, let's say we've got another velocity versus time graph here, and this time I want a constant velocity, zero acceleration. And again, let's assume that this is all happening for an object moving strictly in the x direction. So let's say we have this as our situation. So we've got some sort of velocity, I guess we'll call it v initial, and it also happens to be equal to v final since there's no acceleration. What's the displacement when you have a constant velocity? Well, that's pretty easy. We would just say if my velocity is constant, then my average velocity is just the only velocity I have. So I would just go v initial equals my average velocity equals total displacement over total time, and the total time would just be whatever this gap is. That's going to be delta t, t final minus t initial. If t initial is 0, then I can just say t final is equal to t minus 0 equals t. So we can say that this is just equal to delta x over t final minus 0 equals delta x over t final, which I'll just rename as t for the sake of simplicity. If I take this first and last part over here, and I do v initial equals delta x over t, and I multiply the t over, I get my delta x. So v initial times t, or just v times t if you prefer, is equal to delta x when the velocity is constant. Okay, but let's take a look at the graph and let's see what else v initial times t is equal to. V initial is basically the height of this rectangle. If I were to draw a line here, this height is equal to v initial, and this width is equal to delta t, or just t as we called it. So area under a velocity versus time graph appears to give us displacement. And that should make sense because the height is measured in, I guess this would be in meters per second, and the time is measured in seconds. And if I multiply height by width, if I multiply meters per second by seconds, then the units of this area are going to be meters per second times seconds. The seconds cancel out. Meters per second times seconds. The seconds cancel out and you're left with meters. Those are units of displacement without regard to the direction, but units of displacement nonetheless. So area under a velocity versus time graph is equal to displacement. Okay, then what is the area under a velocity versus time graph where the velocity is not constant, where the velocity is changing? It's a little bit more complicated. Did I say that the acceleration isn't? No. What's the area under a velocity versus time graph where the velocity is not constant? Well, if the acceleration is constant, then we have the next best thing because we actually have nice shapes that we can work with. So this can actually be split into two parts. The total area under this orange line can be split into two parts. One part is this rectangle, which I will shade in green, and another part is this triangle, which I guess I will shade in red. And the areas of each of those shapes should come out to be in units of meters. Let's work them out. So first off, we've got, I'll work with the rectangle. What is its width? What is its height? Well, its width is just all of this. So I guess I'll call it width equals t final minus t initial being 0, t final minus t initial, which is 0, just equals t final, which I'm just going to call t yet again. And the height is v initial. Okay, this looks familiar. It's basically the same thing we got over here, v initial times t. So area of the rectangle is equal to v initial times t. So far, we've got the same thing as if we had a constant velocity, but we know if we have an acceleration, in this case a positive acceleration, we are going to get more. If you just think about it intuitively, the amount of displacement you cover when just moving at a constant velocity is just a part of what you would get if you had a velocity that's actually increasing. If your velocity is increasing, then you ought to get more displacement compared to a velocity that's just constant. That makes intuitive sense to me. So let's go ahead and figure out what the area of this triangle is going to be. If I do area of a triangle is 1/2 base times height, a triangle is 1/2 base times height. Well, the base is the same as the width of the rectangle underneath it, so that's still going to be what we called t. That will be the base, so 1/2 base, which is t, times the height. What is the height over here? What is this height? Well, we labeled it earlier. It's v final minus v initial. This was the height. The height is v final minus v initial. And if we look at the units, we see this is going to be in seconds, and then you've got meters per second minus meters per second. That's still going to be in meters per second. So we're still getting meters per second times seconds, which is equal to meters. So yes, our area is coming out to the correct units. But this isn't really the nicest looking expression. Let's see if we can substitute our v final minus v initial with something else. We already have it right up here. When we were rearranging the acceleration formula. We started with the average acceleration formula, v final minus v initial over t final minus t initial. Then we went to this, simplified the bottom to just a t since t initial was 0. And then we multiplied the t over, and we ended up with this, v final minus v initial, the change in velocity, is equal to the acceleration times the time. So we can actually make that replacement right now, and we get 1/2 t times acceleration times time. If I multiply this t into the t in the parentheses, I get t squared. So I get the area of my triangle as 1/2 and then a and t squared. Okay, so putting it all together now, the total displacement, the total change in position, is going to be the area of the rectangle plus the area of the triangle, equals area of the green rectangle plus the area of the red triangle equals v initial times t plus 1/2 a t squared. You might see teachers write this a little bit differently, so let me first off write it without this in-between step. Delta x equals v initial times t plus 1/2 a t squared. Assuming a constant acceleration, this would be our second equation of kinematics, our second equation of constant acceleration, or uniformly accelerated motion equation, whatever you want to call them. But maybe your teacher writes this differently. Maybe your teacher splits up the delta x into x final minus x initial, and then adds the x initial over to the right-hand side so that you get x final equals x initial plus v initial times t plus 1/2 a t squared. And maybe some teachers will write x final as just x, and they'll write x initial as x0. So you might see other teachers writing it like this, x equals x0, and they probably use v0 as well instead of v initial, plus 1/2 a t squared. And that's fine, as long as you understand that all of these equations are equivalent. I like to use this version because more often than not, you don't have an initial position to work with, and if you do have an initial position to work with, an initial position that's not 0, then all you have to do is add that to whatever change in position you get, and you're good to go. So I wouldn't sweat the details on this. Use whatever your teacher uses, obviously, just for the sake of, giving them an easier time grading your papers. If you make their job of grading you easier, they're probably not going to grade you as harshly. That's the unfortunate nature of some teachers. They tend to be strict on things like that. So yeah, for the sake of your own grade, just adapt to whatever your teacher does, but you will see differences in these equations depending on, whose videos you're watching on YouTube if you're trying to learn from multiple sources. And you might also see them differently between different textbooks as well. So it's good to be aware of those subtle little differences. They're just a matter of preference at the end of the day. As long as you can instantly recognize when someone is using the same equation as you, just in a different form, you'll be good to go. But yeah, that's our second equation of kinematics. Now we want to get our third equation of kinematics, where does our third equation come from? Our third equation is not really a necessary equation. We can just make do with these two equations, and these are actually enough for us, but we often have cases where t, the value of t, is not given to us in a problem, and if you don't have anything other than these two equations, then that just means you're going to have to use the two equations together and eliminate t, and it's more work than it's worth. So what if we did that work ahead of time? What if we created an equation that eliminates time in advance? That's exactly what we're going to do next. So we don't have to look at the graph anymore. Let's rewrite our first and second equations and see what happens if we try and combine them in such a way that we can eliminate the time t. Oh, right, and also, even though I ranted about this earlier, memorize. Memorize, and if you remember where it came from, that helps with the memorization. It came from the area of a rectangle plus the area of a triangle, and the area of the rectangle is just how much displacement you would have achieved if you remained at your initial velocity for that period of time, so that shouldn't be too hard to piece together on the spot. And the other one comes from a triangle. You can probably guess. Well, let me think about this. How do I want to? Yeah, from the fact that it comes from from a triangle, that's where the 1/2 comes from, right? 1/2 base times height. So that's how you remember that the 1/2 is in it. And then the AT squared, you can just check based off of the units. Acceleration is in units of meters per second, or meters per second squared, times time squared. Well, that's seconds squared. Seconds squared cancel with seconds squared, and that gives you units of meters. So yeah, it all checks out. As long as you look at the individual pieces of the equation and really sit there and think about it for a good 5 to 10 minutes, you will see that it does make sense, and that is what will help you remember them. It's not just banging your head against the textbook until the equations stick. Actually think about the equations and convince yourself that they make sense, and that will help them stick in your memory much better. Anyway, I was going to combine these two equations to get the third equation of kinematics. So what we want to do is eliminate time, and usually the way to solve systems of equations in physics, the most commonly used method, is simple substitution. So I want to eliminate t, which means I want to substitute for time. The second equation is quadratic in t, so that's going to be a hassle to work with if you're trying to isolate the t over here. In the first equation, isolating the t is much easier, so that's what I'm going to do. I'm going to go ahead and try isolating t from the first equation. So I can subtract v initial and divide by a. V final minus v initial equals at, and then if I take it one more step, v final minus v initial over a equals t. Okay, now that I have this expression for t, I can go ahead and plug it in for t over here and over here. So delta x equals v initial times, t is replaced by v final minus v initial over a, plus 1/2 a times t squared, which is going to be v final minus v initial over a all squared. Okay, I see this a in the denominator. That's going to give me some trouble, so I'm going to go ahead and multiply everything in this equation by a to get rid of that denominator. So I'm going to have a times delta x equals a times this expression. The a would just cancel out. V initial, you know what, I'll write the a times v final minus v initial over a. We'll cross it out in the next step. Plus over here I'm going to have 1/2 a squared, and then v final minus v initial squared over a squared. Right? If I square an expression, exponents distribute over multiplication and division, so the square of a quotient is the quotient of the squares. I can just do top squared over bottom squared, and that is an equivalent expression. So we multiplied everything by a delta x there, we multiplied the v initial by an a here, and we multiplied this a by another a here. Okay, this a, when divided by this a, will cancel out. This a squared will cancel out with this a squared. And now I have a delta x equals, this is going to be a very ugly expression, but it will simplify nicely in the end. V initial times V final minus V initial times V initial if I distribute this V initial from the outside. Okay, and I'm going to put that in brackets for now, just to keep things organized. We don't actually need it, but just for the sake of organization, plus 1/2, let's see, V final minus V initial all squared. I should use brackets for this as well. I mean, I could have used parentheses, but if I used brackets for this, I might as well stay consistent. V final minus V initial times V final minus V initial. Shouldn't be your first time foiling an expression like this. You get V final squared minus 2 V final times V initial, or V initial times V final. It doesn't matter, but I'm going to do initial before final because that's what I did over here. And then plus V initial squared. Okay, I want to distribute the 1/2, so I get a delta x equals V initial V final minus V initial squared plus 1/2 V final squared Actually, wait, do I want to distribute the 1/2? Actually, I think the better move would be to just multiply everything by 2. Yeah, I think that's what I'm going to do instead. So scratch what I was about to do. Multiply everything by 2. And so we get, let me switch colors. Multiply everything by 2. So we get 2a delta x equals 2 v initial v final minus 2 v initial squared. That's my first bracket. Plus 2 times 1/2 cancels the 1/2, and everything else just stays the same since the 1/2 in front of it got canceled out. And let's see what we can do with this. So 2v initial v final and minus 2v initial v final, those cancel each other out. And then I'm left with negative 2v initial squared and positive 1v initial squared. Negative 2 and positive 1 is negative 1. And then I've got a v final squared. So it looks like this simplifies to 2a delta x equals v final squared is positive, so I'll put that up front. And then minus 2 and plus 1 is minus 1 v initial squared. Okay, add v initial squared. On both sides, and you end up with this expression, which I prefer to rewrite with the v final squared on the left-hand side. V final squared equals v initial squared plus 2a delta x. This is our third equation of kinematics. I guess I will circle this in, how about this blue color? This is our third equation of kinematics. And these three equations are more than enough. The first two are already enough on their own. This third one is a bonus that saves you time in situations that, ironically enough, don't give you information about the time that an object is moving. In order to work with this equation, you would only need 3 pieces of information out of 4. You've got v final, v initial, acceleration, and displacement. As long as you know 3 out of those 4 things, you can plug them into this equation to solve for the 4th one. Now there is a 4th equation of kinematics, which is very highly situational, and you don't really need it, but we can discuss it anyway. So let us draw yet another graph. I know. Some people are already tired of seeing so many graphs. Let us draw yet another graph. Oh, and by the way, this would still work. All of the math we've done here would have still worked if the acceleration was negative. It would have still worked if this line was going down instead of up. You would just substitute in a negative value for the acceleration, and I guess if I wanted to draw something with a line going down, maybe I'll draw that later for those who aren't fully convinced. But let me finish up what I'm doing here first, and then we'll discuss that, just in case you're not entirely sold on the idea. But let's once again assume a positive acceleration, just because that's easier to work with. Let's say our initial velocity is over here, and our final velocity is up here. And let me do the dotted line thing again. Yeah, something like that. And let's go ahead and draw a straight line between those 2 points. What color do I want to use here? Let's use the navy blue. Okay, something like that. Let's say I want to calculate the average velocity between these 2 points. Well, you might remember something I said last time about averages. The average value is a value that, if you treat it as if all the values were the average, you get the same total. In this case, the total in question is the displacement. So, at what velocity must I move in order for the total displacement to be the same? So we've got some sort of area under this curve. we've got some sort of area under this, well, I guess it's not really a curve because it's a straight line, but you know what I mean. We've got some sort of total area between this rectangle and this triangle. And we want some sort of velocity value that's clearly going to be somewhere between v initial and v final. It's going to be somewhere in here. In fact, it's going to be exactly halfway in between, as we will soon prove. This is v average. And we want it such that the area under the v average line is equal to the same total area of this triangle and this little rectangle over here. Maybe I should have drawn v average in a different color. So what I want is for the area under v average, which is going to be this green rectangle, plus, let's use this pink rectangle. I want the green area plus the pink area to be equal to the triangle area plus the pink area. So for the triangle, I guess I will use, let's use purple. So for the triangle, I will use purple over here. So I want the green rectangle plus the pink rectangle to be equal to the, I want a green plus a pink to be equal to the purple triangle area, a purple plus a pink. Well, since they both include the pink area, I can eliminate that from both sides of the equation. So all that's really needed is for the green area to equal the purple area. All that's really needed is for the green area to equal the purple area. And the way you would achieve that is if you cut off this part of the triangle over here. If you were to cut off this section, let me highlight it in yet another color. If I were to cut off this section, I'll highlight it in orange. If you were to cut off this piece of the triangle and pick it up and flip it over, it would fit exactly into here. As long as you make the cut exactly at the halfway point between v initial and v final, as long as you cut it at half height. So let's see equation-wise how we would make this work. So area of the purple triangle is going to be 1/2 at squared, right? We did that over here. We did area of the triangle is equal to 1/2 at squared. 1/2 the acceleration times time squared. Or, actually, I think I would prefer to have it in its original form. Before 1/2 at squared, it was 1/2 t times v final minus v initial. Yeah, let's keep it in this form for now. So, area of the purple triangle, 1/2 v final minus v initial all times t. I wrote that in a slightly different order. I wrote the t at the end instead of the front, but should be the same thing. And then the green area should be a width of t, right? The width is going to be just t. And the height is going to be the difference between v average and v initial. So this is going to be v average minus v initial. V average minus v initial times t. Okay, well, since they're both times t, I can cancel out the t. So now I have v average minus v initial equals 1/2 v final, if I distribute the 1/2, minus 1/2 v initial. And if I add v initial to both sides, then I get v average equals 1/2 v final, and then minus 1/2 plus 1. Negative 1/2 plus 1 is positive 1/2. Positive 1/2 v initial. So we factor out the 1/2 now, and what we end up with is v average equals v final plus v initial over 2. So under constant acceleration, and only under constant acceleration, well, not only under constant acceleration, this could also happen if you have some very weird and unrealistic acceleration situation, but in all realistic situations where an object's velocity changes continuously, only under constant acceleration is the average velocity the average of the velocities. In most normal cases you will encounter, the only way that you can average two velocities and let that be equal to the average velocity is if the acceleration is constant. If the acceleration is not constant, and you have no reason to assume it would be constant, then what I said last time still stands. The average velocity is not the average of the velocities, and the average speed is not the average of the speeds. And you might remember last time we explained why that is. It's because average velocity is a weighted average, and it is weighted by time, counting all of the different velocities equally and dividing them by the amount of by the total number of velocities doesn't usually work, because each velocity contributes for a different amount of time to the total. So then, if we can weight the initial and final velocities equally here, then does that mean that all of our velocities are weighted equally? That's what this would imply, so let's try and see if we can make sense of that. Let's say our initial velocity was, let's say our initial velocity was 3 meters per second, for example. And let's say our final velocity is let's say it's 8 meters per second. Do we spend equal amount of time at each and every velocity on the way from 3 to 8? Well, it should be, to some of you, it might be really obvious just from the shape of the graph that, yeah, if it's going in a straight line, then each value on the way from v initial to v final is visited for the exact same amount of time, a very, very microscopic amount of time, because the velocity is always changing. But basically, you spend the same amount of time, so you start at 3, and then 1 gazillionth of a second later, you're at 3.00, a bunch more zeros, and then eventually there's a 1 there. And then the next instant, you're at 3.000, a bunch more zeros and 2, and then you're at 3.0000003. You are at each of these velocities for the same amount of time. So yes, in this case, all of the velocities are being weighted equally. Every velocity you have along the way from here to here, you're spending the same amount of time at each velocity, so they are each weighted equally. So you can just do v final plus v initial over 2 and get your average velocity that way. And once you get your average velocity this way, you can use the other formula we know for average velocity. Average velocity equals total displacement over total time. We're just simplifying it down to t instead of delta t, as we have been doing today. And if I multiply by t, then I get v average times t equals delta x. If I replace v average with this, then I get v final plus v initial all over 2, and some people will write it in parentheses and put the 1/2 in front of it instead. Either way, times t is equal to delta x. This is what some people consider to be the fourth equation of kinematics. I don't really use it all that much because it's very, very situational, and even in the situations where you can use it, it's really more of a shortcut. So this would be the last equation to commit to memory, and really it's not even, at least to me, it's not even an equation to remember. For me, it's a concept to remember. As long as you remember the concept that under constant acceleration, the average velocity is the average of the initial and final velocities. As long as you remember that concept and you understand what averages are, you already have all the pieces. You can just reassemble it on the spot so that you don't have to memorize it. At least that's how I remember it every time. I didn't use flashcards and stare at this for hours and days until it stuck in my head. I just remember the idea, and I always just quickly reconstruct it on the spot within seconds. Maybe I should make a video on the topic of memorization. I think I already have a script for that video from a long time ago that I just never got around to recording. I'll have to go and dig that up. I'm pretty sure I have it on one of my computers. Anyway, where do we want to go from here? So we have our equations of kinematics now. I guess it's time to... Oh, right. For those of you who might be bothered that I only used graphs with positive slopes, let's see how this works out in situations where the slope is negative. We can still have quote-unquote negative area here. It's not that area as a concept can be negative, it's just that the thing that area on our graphs represents can be negative. In this case, area is representing displacement, and we can certainly have negative displacement. So area below the horizontal axis counts as negative quote-unquote area. Let's see, what if I had my v initial is over here and my v final is all the way down here? And my v final is all the way down here. And let me go ahead and draw a line there. Trying to line it up so that it doesn't slant. Okay, something like that. And then that should be good. Oh, wait, well, actually no, I don't need to draw the rest of that. I can just draw a line connecting these two. Let's see. That should be good. Good enough, at least. Wait, I should just draw it as a straight line. What am I doing? Why was I doing dotted lines there for a minute? Okay. So what about something like this? Well, you still have the same idea. You would still have the same ideas. They still work. In the case of a negative acceleration. So you would have your v initial times t. You'd have your area of this rectangle. So the height of this rectangle is still v initial, and the width of this rectangle is still the amount of time t. And then you would have the area of the triangle. So the area of the triangle is two parts. At first, the velocity is positive. Let me not use green. Let's use orange. At first, you've got some positive. Wait a minute. Let me think about this. Actually, no, I guess it would be subtracted. Hold on, I need to think about this before I say something confusing. So the purple rectangle is how far you would have traveled, the displacement you would have achieved if your velocity was constant. But of course, what you actually get is less than that. So your actual area is going to be, your actual displacement is going to be this orange triangle over here, plus, or I guess you could say minus, since it's a negative triangle, minus this area over here. So we would have this initial area is positive, which makes sense to me. You start at a positive velocity. Even though you're slowing down, you are still moving forward for a while. Once you get to this point, this is the point where you stop to turn around. So this is where your displacement peaks and then starts to decrease. And then after some amount of time, let's say around here, I want to say, you would have walked back just as far as you walked forward, and then everything beyond that point would be walking behind the starting line. So everywhere after whatever this arbitrary line is, well, I guess it's not arbitrary, but you know what I mean. I drew it arbitrarily, but it should be somewhere around there. Everything past that line in this orange area should be negative overall displacement. Now let me try and make sense of this in terms of that purple rectangle. I guess I've always just been taking it for granted that it will work out in the negative case, which it does, but I actually never bothered to do this before. This is getting interesting. Let's see. So I guess what we could do, so 1/2 AT squared would be the area of this triangle, over here. Which has a base of t and a height of, I guess, v initial minus v final. I'm just going to call it v final minus v initial and then put it in parentheses and put a negative in front of it. How do I... Let's see. So my claim is that v initial times t, this purple area, plus 1/2 times this thing, 1/2 times t times negative of v final minus v initial. My claim is that this is equal to this orange area minus this orange area, so I guess I would need to figure out where this point is. Okay, actually this is an interesting problem. Let's go ahead and do it. I wasn't expecting it to take this long, but I don't mind sparing the extra time to do this. It might be worthwhile for some people just to untangle some knots in our brains. How would I define this over here? This is going to be some fraction of t. What would I call it? This would be at the point, I will call it t star. This will be at some sort of time t star. So I've got the area of the first orange triangle would be 1/2 of its height from the horizontal axis would be just v initial. So we've got 1/2 base times height. 1/2 the height is v initial, and then the base is just going to be t star, right? The distance from here to here is just going to be t star. And then minus this orange triangle is going to be 1/2 its height is going to be v final, right? This is just going to be v final. And then its base, this whole thing, I know that's kind of hard to see since I'm drawing it over the axis, that would be t minus t star. That would be t minus t star. And how do we grapple with this t star thing? Because we definitely need to eliminate that. I'm guessing I would just use my first kinematics equation here, so I would do v final equals v initial. Actually, wait, v final, no, hold on. No, at t star, the quote-unquote final velocity is at 0. Your velocity is at 0 at time t star, so what I should do is velocity 0 equals velocity initial plus acceleration times t star. Here we go. And then subtract v initial and divide by a, and we get t star equals negative v initial over a, which does make sense. The time is a positive value. If you do a negative of v initial, negative of a positive initial velocity divided by an acceleration which is negative, then yeah, this is actually a negative over a negative, which is a positive. So yes, this does work. Okay, so let's see what we can do with this. So circle that off. And let me see what we can make of this. Are these two expressions actually equivalent? V initial t plus, or I guess I could make that minus, plus 1/2 t times negative v final minus v initial. Well, we saw, where was it? Over here, v final minus v initial is equal to at. So I'm going to go ahead and replace the negative of v final minus v initial with the negative of at. So this is just going to be negative at. equals 1/2 v initial times t star, which I now know is negative v initial over a, minus 1/2 v final times t minus t star, which is going to be t plus v initial over a. I have a feeling I might have screwed something up along the way here, but we will see what we get. And if I don't get anything that makes sense, I will tinker around with this later and have an answer next week or sooner. You're not the only one who starts to lose confidence when an answer starts looking really messy like this, but one of the things that physics teaches you is a lot of times to get to an answer for something like this, you need to just press on and see how far your equations will go. So, what do I want to do here? Is there anything I can simplify? We'll see. V initial t minus 1/2 a t squared equals I feel like I'm going to have to multiply everything by 2 at some point just to get rid of those fractions. Equals 1/2, or maybe minus 1/2 v initial squared over a minus 1/2 v final t, and also minus 1/2 v initial v final over a. I think I might be able to see where this is going. If I multiply everything by 2, I get 2 v initial t minus at squared is equal to negative v initial squared over a minus v final t minus v initial v final over a. And I am thinking if I replace this t with where was it? I had it here somewhere. I think it was back when I was, yeah, t is equal to v final minus v initial over a. So if I simply replace t with v final minus v initial over a, I think I might be able to get something here. 2 v initial t minus a t squared equals negative v initial squared over a minus v final times t is equal to v final minus v initial over a minus v initial v final over a. Okay, I can multiply everything by a and then see if I can do something to simplify this right-hand side. So I would get 2 v initial times t. Actually, wait. You know what? I'll factor out the 1 over a on the right-hand side. Minus a t squared equals, in fact, I will factor out negative 1 over a. Negative 1 over a times, we have v initial squared plus v final times v final is v final squared, and v final times negative v initial is minus v initial v final, and then plus, because I factored out the negative, v initial v final, plus v initial v final. These cancel out. So now I've got v initial squared plus v final squared times negative 1 over a on the right-hand side. And I'm somehow supposed to prove that this is equivalent to this. I mean, I feel tempted to invoke the third kinematics equation here, but that was also derived from our first two, and we're trying to prove that the second equation still works for this situation, so using the third equation would be assuming the thing that we're already trying to prove. I suppose I could substitute the t's, but I feel like I'm missing something far easier than that. Okay, 2 v initial t what do I want to do here? Actually, I think I'm going to actually multiply the a, so multiply the negative 1 over a. So yeah, multiply by negative a. Canceling negative 1 over a means multiplying the whole equation by negative a. Okay, so negative 2 v initial t times a. And then this becomes plus a squared t squared equals v initial squared plus v final squared. This turned out to be a lot longer than what I expected. T times a, well, we know what a times t is equal to. It's equal to v final minus v initial. So I can do a squared t squared. I'm going to write that first. So that's going to be at squared, and at is v final minus v initial. So a squared t squared is v final minus v initial all squared. And then minus 2v initial times at, so that's going to be another v final minus v initial there, equals v initial squared plus v final squared. Is there a way to simplify this without distributing? I feel like there should be something I can do here. I feel like I might be able to solve this by grouping. I can factor out a v final minus v initial there. What would that do for me? If I factor out a v final minus v initial, then I would get, well, a v final minus v initial minus 2v initial. Does that help in any way? Oh, I think it does. I think I'm seeing where this is going. So I would get v final minus v initial times v final minus v initial minus 2 v initial Wait a minute. If I were to open those parentheses, I would have minus 3 v initial, which doesn't sound right to me at all. Equals v initial squared plus v final squared. Yeah, this is getting rather ugly. And apart from just foiling everything and hoping for a lot of stuff to cancel out, I don't see some sort of clever simplification I can do. It's not coming to me right away. I thought I was seeing something looking 2 steps ahead, but now that I've actually done this step, I don't see it anymore. Did I factor incorrectly? That doesn't appear to be the case. Oh, and I forgot the square there. Yeah, I don't know. I think I'll actually want to come back to this one later. Well, let's try the extreme solution first. Let's see if actually foiling all this. So forget this. We'll start back from here. And let me actually foil this whole mess and see if the left-hand side equals the right-hand side. So if I foil that, I get v final squared minus 2 v initial v final plus v initial squared that's a very awkward looking 2 minus 2 v initial v final, and then if I subtract, well, negative 2 and negative 1 becomes positive 2, so plus 2 v initial squared equals, it's supposed to equal v initial squared plus v final squared. We'll see if that's actually the case. Well, I can cancel v final squared on both sides. And I'm getting the same problem of this 3v initial squared thing. I've got 3v initial squared. If I combine this with this, and then minus 4 v initial v final, and that's somehow supposed to equal v initial squared. If I cancel v initial squared on both sides, then that leaves me with 2v initial squared minus 4 v initial v final has to equal 0. If I factor out 2v initial, then I'm left with v initial minus 2v final has to be equal to 0, which would imply that either v initial is equal to 0, which is not true, or v initial is equal to 2v final, which is not necessarily going to be true either. Okay, I must have screwed something up here. I don't know whether it was somewhere among my steps or the way I formulated the problem. Maybe I missed a negative somewhere and screwed this all up. But I will tinker around with this later and see what I can piece together. I was expecting it to be a much simpler ordeal than this. Let's see if I can at least make a geometric argument here. the area of this purple rectangle minus the area under this green triangle is equivalent to this first orange triangle minus this second orange triangle. Is there a way I can justify that just through the geometry, just looking at the drawing? There probably is, but I'm not seeing anything obvious that stands out to me. I think a better use of our time at this point would be to just continue with what I had originally planned after proving the three equations, which is actually practicing using them. So let's go ahead and look at some problems involving the equations of kinematics. I think I want to use problems from one of my physical textbooks, so let me go and grab one of those real quick. All right, let's see what we can pick out from here. And we might also look at some of the problems from the OpenStax textbook, since I'm sure some students might have questions on a few of them. I'll take a glance at those later. But let's see what we can do with these physical textbook problems first. We've got, this problem says a truck covers 40 meters in 8.5 seconds while smoothly slowing down to a final speed of 2.8 meters per second. Part A, find the truck's original speed, and Part B, find its acceleration. So I guess we're starting off with the hardest type of kinematics problem, or one of the hardest types, because your unknowns are the initial velocity and the acceleration. And you may have noticed the wording of the textbook, it used the word speed, so you kind of have to interpret the problem carefully and understand that if the problem is referring to an object's speed, but you can reasonably assume that the object is moving in a fixed direction, then that speed can easily be turned into a velocity just by you deciding that the forward direction of the object's motion is the positive direction. I guess you could make it the negative too if you're feeling dangerous, but positive would be the default assumption for the direction an object is moving when the problem doesn't exactly specify. I would assume this truck in the problem is just moving on a straight road, unless I'm told otherwise. So a truck covers 40 meters. We will assume this truck, I guess I'll draw it for the purpose of visualizing what we're working with. I'm assuming it's like, a small truck and not an 18-wheeler. But we've got a truck. It moves 40 meters in 8.5 seconds while smoothly slowing down to a final speed of 2.8 meters per second. It's probably not going to magically go backwards. This person, I would reasonably assume is just pumping the brakes, and brakes don't make you go backwards, they just slow down your forward motion. So I would assume their initial and final direction is forward or positive. So I have their V initial currently unknown, V final, they said is 2.8 meters per second. Well, they said 2.80, but that's for the teachers that care about the sig figs. We were given, I guess this would be a displacement in the positive direction, a displacement of positive 40 meters. And we were given, we don't know the acceleration, we were given the time is 8.5 seconds. It takes 8.5 seconds for this slowdown phase to occur, and in those same 8.5 seconds, 40 meters of displacement is achieved. Okay, so we have 3 of our kinematic variables. As long as you know 3 out of the 5, you can always solve for the other 2 using your first 3 kinematics equations, and sometimes in some situations it may be helpful to use the 4th to speed up the process. Anyway, actually I think this might be a situation where the 4th equation would speed things up, but let's take a look at the strategy that you would use if you didn't know about that 4th equation. So I have 2 unknowns. My 2 unknowns are v initial and the acceleration. If I write down my kinematics equations, v final equals v initial plus at, v final equals v initial plus at, and second equation, displacement, equals v initial t plus 1/2 at squared, and third equation, v final squared equals v initial squared plus 2a delta x. Usually the strategy for picking which equation to use is you look at the 3 kinematic variables that you do know, and you look for the one that involves all 3 of those and has one more variable that is the one that you don't know that you want to solve for. Unfortunately, no matter which of these equations I pick, if I pick the first one, I know v final and I know time, but I don't know v initial and a. And second equation, same problem. I don't know v initial and a, I know everything else, and third equation, I don't know v initial and I don't know a. So no matter which equation I pick, I'm going to have 2 unknowns. Well, if you have 2 unknowns, you need 2 equations to solve. So that's what I'm going to do. I'm going to pick 2 of them, and I think the 2 easiest ones would be the first and second, but you're more than welcome to do first and third or second and third if that's your preference. You might, over time, develop a strategy for which ones might be the easiest to work with, depending on what information is given. For example, students very quickly learn that when time is unknown, solving for it using the second equation is probably best avoided because you would have to do a quadratic formula, which sometimes is unavoidable, but if you can't avoid it, some students would end up developing the strategy of just using the third equation and then using the first equation to solve for time instead. So those are just some things that you'll learn through practice. Anyway, where was I? First and second equations. So I'm going to use the first equation along with the second, and I'm going to plug in these values where they are known. So v final being positive 2.8 equals v initial, which is currently unknown, plus acceleration is currently unknown, times time is 8.5. So I'll write the 8.5 first and then the a. And then second equation, we've got positive 40 for the displacement equals v initial times 8.5 plus 1/2 times the acceleration times 8.5 squared. So I'll write the 8.5 squared first, and then the acceleration. I'm not going to square the 8.5 right away because we might be able to simplify something here. In fact, I think I can already see what can be simplified. If I divide by 8.5 here, I get 40 over 8.5 equals V initial plus 1/2 times 8.5a. I might actually be able to solve this by elimination instead of substitution, because now I can just do this equation minus this one. And if I do that, if I do top minus bottom, I would get 2.8 minus 40 over 8.5 equals V initial minus V initial is gone, and 8.5a minus half of 8.5a, well, 8.5a minus half of itself equals the remaining half, so that's 1/2 of 8.5a. See, this is why you might not want to reach for your calculator right away. Because if I had plugged this into my calculator, I probably would have missed this nice little shortcut. But now we have the acceleration. And was that the first thing they asked for? No, the first thing they asked for was find the truck's original speed, but that's okay. That happens a lot in physics, where to calculate part A, you need to solve part B first, and that's something that they will do on purpose in textbooks and on exams, because they want to test your physics knowledge. They want to test, do you understand that you need X information before you can solve for Y information? And of course, I guess we could have also I could have multiplied this first equation by 1/2 and then subtracted that from the third equation, and I could have eliminated the acceleration and solved for V initial first. We definitely could have done part A and then part B, but I think this might be the easier way to go about it. So yeah, you don't necessarily have to solve the parts of a problem in order. Let's go ahead and plug in the numbers we do have now. So where's my calculator? There it is. So I've got 2.8 minus 40 over 8.5. Whoops, accidentally deleted it. 40 over 8.5. And then I want to, well, actually wait. And then multiply by 2 and divide by 8.5. So take all of that and then multiply it by 2 and divide it by 8.5, and I get an acceleration of negative 0.448 approximately. I get an acceleration of negative 0.448 meters per second squared. I probably should have made more room for that. Okay, does it make sense for my acceleration to be negative? Well, yeah, the truck was moving forward. Its initial velocity, whatever it is, it has to be something in the forward direction, which we have indicated as being positive here. So it makes sense that the acceleration would be in the negative direction if the truck is slowing down. Slowing down means acceleration and velocity are in opposite directions. So if velocity is in the positive direction, acceleration must be in the negative. So that so far is making sense. And does it make sense that the number is small? I mean, I guess it is realistic, but we would actually have to see what the initial velocity is. And that is our next task, so let's solve for V initial. Now that we know A, I guess I would use this first equation, might be the easiest way to go about it. So I'll do 2.8 equals V initial plus 8.5 times negative 0.448. 2.8, that's going to be plus 0.448 times 8.5. I'm just taking this, which is going to be a negative, and adding it to the 2.8, and I'm getting 6.608. I'll just round that to 6.61. So V initial is about 6.61 meters per second. 6.61 meters per second. And how do I know what units I'm getting? How do I know what units I'm getting? I guess we could write them into our equations and see how the units work out. I'm not going to do that every time, but it might not hurt to do it the first time. So we had 2.8, which was in meters per second, minus 40 was the displacement, which was in meters, divided by 8.5, that was 8.5 seconds. So meters per second minus meters per second equals, the 1/2 is just a factor from geometry, right? It comes from the area of a triangle formula. It doesn't have any units, so not going to be factored in here. The 8.5 is a unit of time, so that's seconds, times whatever the acceleration units are. I guess I'll just call it U of A, units of acceleration. Okay, when you add and subtract units, the units don't change. If I take 5 kilograms plus 10 kilograms, I get 15 kilograms. If I subtract, same thing. When you add and subtract, you get the same units. So this is still going to be in meters per second. And if I divide both sides by seconds, then my units of A, if I divide both sides by seconds, divide by seconds here, and I guess multiply by 1/2 there, then I get my units of acceleration are in meters per second squared. It's not a bad idea to learn how to do this sort of algebraic manipulation to derive what your final units are at least a few times, because you will have questions, especially in the multiple choice on the exam, that might ask you, what are the units of this quantity in this equation? The one that I know they tend to ask for a lot is the units of constants like big G, the universal gravitation constant. You'll come across an equation, we'll discuss it several chapters from now, where the gravitational force is equal to this constant big G times the mass of one object times the mass of the other object in the interaction, divided by the distance between them squared. And you have to figure out what the units of G are based on the units of everything else in this equation, and that might show up as a multiple choice. Or they might just give you an expression, what units do I get when I multiply these two things and divide them by this third thing? And it might be something that you're not used to seeing, not even an equation that you recognize. So yeah, learning how to work with units like this is not a bad idea. If you've done AP Chemistry, then you might already have plenty of experience doing this, especially from dimensional analysis, though there is more to it, admittedly, than just simple dimensional analysis here. But if you know your dimensional analysis from chemistry, making the leap to deriving units in physics is not that hard. Anyway, let's see what we can ask next. Let me read through these problems and see where I can find a good one for us. We've got 2 cars traveling. Well, I do want to do racing problems, but I don't know if I want to do that right away. The speedboat. Yeah, I mean, it is an easy one, but we might as well look at some easy ones. Okay, so it says a speedboat increases its speed uniformly. That means with constant acceleration. If you see the words, let me switch colors here. If you see the word uniformly, uniformly means something is constant. Something is constant. What that something is depends on the situation. You might have an object with a uniform density. You might be talking about uniform circular motion, or in this case, we are talking about uniform acceleration. The acceleration is constant. So it says a speedboat increases its speed uniformly from 20 meters per second to 30 meters per second in a distance of 200 meters. So they're using the words speed and distance, but if you assume this is all motion occurring in a straight line, then you can use the speeds as the magnitudes of velocities, and you can use the distance as the magnitude of the displacement. Find A, the magnitude of its acceleration, and B, the time it takes the boat to travel the 200-meter distance. So let's see if we can fit all that in here. So it starts with V initial equals 20 meters per second. V final is 30 meters per second. Displacement, assuming this thing moves in a straight line, is 200 meters. And that's all the information they give us. Acceleration we currently don't know, and time we currently don't know. We've got 3 out of 5 kinematic variables. We can solve for the other 2. Always, always, always. If you have 3, you can get the other 2. If they only give you 2, then chances are you were given some additional information somewhere that was not presented to you as a number necessarily. So be on the lookout for that. The most common case of this is when something comes to a stop, that's them telling you V final is 0, or if they say starts from rest, that's them telling you V initial is 0. So sometimes you have to read really carefully. They might be giving you information that you're missing because you don't see numbers being written explicitly in the problem. Anyway, find the magnitude of its acceleration and the time it takes. Find the 2 missing variables. Surprise, surprise. What else could they have asked us? Okay, well, initial, final, and displacement exist in the third equation of kinematics. V final, V initial, and displacement are in the third equation of kinematics, and I only have one unknown there, which is the acceleration, so I can easily solve for it. So let's start with the third. V final squared, which is 30 squared, equals V initial squared, which is 20 squared, minus plus 2 times the acceleration, which we don't know yet, times the displacement, which is 200. I would expect the acceleration to be positive because velocity went up from 20 to 30. I would expect, did I say velocity? Acceleration. I expect acceleration to be positive since velocity went up. Okay, 30 squared is 900 minus 20 squared, that's 400. 900 minus 400 is 500. Equals 2 times 200 is 400, A. and divide by 400, and I get 500 over 400 is 5 over 4 is 1.25, and that should come out in meters per second squared for my acceleration. So let me switch colors for that. .25 meters per second squared. There's one of my answers. I should have made my box a little bit wider there instead of drawing it through the two. That was awful. Okay, and then next they wanted us to find the time. We could use the second equation if you're in the mood for using the quadratic formula. I don't recommend that, but you could do it if you wanted to. Instead, what I would recommend is just using the first equation. So I will do V final, which is 30, equals V initial, which is 20, plus the acceleration, which I now know to be 1.25, times the time, which is currently unknown. 30 minus 20 gives me 10, equals 1.25 times t. 10 divided by 1.25 should be 8. So I get t equals 8 seconds. All right, that was not horrible. Two cars traveling along a straight line. We definitely want to do racing problems, but I don't know if I want to do that right away. I don't know if I want to do that right away. Oh, and we definitely want to do a problem where you've got multiple phases, a trip that has multiple segments to it, or multiple legs to it, as some people will say. We definitely want that, so those are on my radar. But I think first I want to look at this one because we should practice with converting units. This probably should have been in Unit 0, dimensional analysis, but I kind of knew we were going to do this sooner rather than later, so I didn't feel the need to do so until now. It says a Cessna aircraft has a liftoff speed of 120 kilometers per hour. So be careful about the wording. Liftoff. They said liftoff speed. .120 kilometers per hour. So two things stand out to me right away. First, they use the word liftoff speed, so we don't know right away, does this mean the starting velocity or the final velocity? It depends on whether the next piece of information involves how much faster or slower it is after it lifts off, or if the question is about it getting ready to lift off. We don't know if this is before or after yet. We can continue reading the problem to figure that out. So that's the first problem. The second problem is the units. I'm used to meters per second. In Physics 1 and Physics C, you get used to meters per second, so this might need to be converted. Part A says, what minimum constant acceleration does the aircraft require if it is to be airborne after a takeoff run of 240 meters? Okay, so now they are telling us this airplane has 240 meters of runway. I guess I'll try my best to draw an airplane here. And I guess I'm going to draw some really exaggerated landing gear. Do they have landing gear in the back? Why am I blanking on this? I even worked with airplanes. I should know this. I feel embarrassed now. Probably should. I'll just draw some wheels in the back. And then I'll do a Google search later and probably facepalm once I realize I did something horribly wrong. Anyway, so it's going to roll on its wheels for 240 meters, and by the end of that 240 meters, it better be at 120 kilometers per hour in order to fly properly. And once we get to the fluids chapter for AP Physics 1, we will gain a better understanding of why planes require a certain amount of speed in order to be able to take off in the first place. I can give you a little bit of a preview. It creates a difference in pressure from under the wing versus over the wing, and the greater pressure under the wing is what helps lift the airplane up. But to create that difference in pressure, you need a high enough speed. And that's all I will say about it for now. So the understanding then is that this airplane starts from rest. They didn't explicitly tell us this, but V initial equals 0. It has to. You've got an airplane that's just parked at an airport, and then the engine starts and it speeds up, and by the end here it needs to reach 120 kilometers per hour, and then it can lift off. So let's see, they said, what minimum acceleration does the aircraft require if it is to be airborne after a takeoff run of 240 meters? So 3 pieces of kinematic information need to be known, and we have them. The one that students miss is V initial needs to be 0. This is just derived from common sense. V final is 120 kilometers per hour. I'm probably going to want to convert that. The displacement, airplanes usually just go on a straight runway, so if they move in a straight line, the distance of 240 meters is also a displacement of 240 meters in whatever direction this pilot considers forward. So that's 240 meters. And then acceleration is unknown and time is unknown. So the way to decide whether or not you need to convert your units is by looking at the units of all the other information you're given. There are no units for V initial since it's 0, and the displacement is given in meters, so either I convert the displacement to kilometers, which I guess would work, or I convert the kilometers per hour to meters per second. Meters per second would probably be the better way to go, because if we're later going to have to calculate the takeoff time, do you think it's practical to calculate the amount of time it takes an airplane to take off in hours rather than seconds? An airplane is probably going to take off in no longer than maybe, depending on the length of the runway, a minute or 2. So I think measuring the takeoff time in seconds is more practical. I don't think point whatever hours is a very sensible unit to use here. So I'm going to convert my kilometers per hour into meters per second. And the way to do that, in case you haven't learned dimensional analysis, here's the basics of it. So you start with 120 kilometers per hour. And here's what you do. You multiply by a bunch of fractions known as conversion factors. So first I need to, well, it doesn't matter what order I do it in, but I want to eliminate kilometers first and replace it with meters, and then eliminate hours and replace it with seconds. So kilometers, I know that 1 kilometer is equal to 1,000 meters. you should just know that a kilo is 1,000. I would hope you know your scientific prefixes, kilo and mega and milli and centi and all of those. If you don't know them, then usually they'll be like in the front or back cover of your typical science textbook, or sometimes they might be in like the first couple pages. Or, you can just go to Google and type scientific/metric conversions and memorize them from there. They're all easy numbers. They're just powers of 10 that you might want to know. But yeah, 1 kilometer is equal to 1,000 meters. And I am allowed to do this multiplication. I'm allowed to do this for the same reason that I'm allowed to do, if I was doing like, 1/2 plus 1/6, I'm allowed to multiply the 1/2 by 3/3 to turn this into 3/6, because multiplying by 3/3 doesn't change the value of 1/2. I'm multiplying by 1. If the top and bottom are equal, then this fraction is equal to 1, and multiplying by 1 doesn't change things, so it's perfectly allowed. Well, what about here? The top and bottom are equal. 1,000 meters is equal to 1 kilometer, so this fraction is just equal to 1. I am allowed to multiply by it. That is all there is to it. So that cancels out my kilometers and gets me meters in the top. Okay, so I've dealt with kilometers. Now let's deal with the hours. You could have done this first. You could have dealt with the hours before the kilometers. It doesn't really matter. But hours, I can do, well, I want to cancel the hours from the bottom, so I want hours in the top here. And I want to say 1 hour is equal to 60 minutes. And now I've canceled my hours, but I have minutes. So I want to get rid of minutes and replace them with seconds. And I know that 1 minute is equal to 60 seconds. So cancel the minutes now, and you've got seconds in the bottom. Meters in the top, seconds in the bottom. This is meters per second. Let's put all this in the calculator and see what we get. 120 times 1,000 times 1 times 1, so 120 times 1,000. Divided by 1, divided by 60, and divided by 60 again. Be very, very careful here. I know some people will write this as divided by 1 times 60 times 60, and because of order of operations on your calculator, you're going to get the wrong answer. Be very, very careful about that. What I would recommend, actually, is if your calculator has a fraction mode, I would use this instead. 120 times 1,000 over 1 times 60 times 60. This would be the safest way to go about it if your calculator has this feature. Otherwise, what I would do is just use parentheses. 120 times 1,000 divided by parentheses 1 times 60 times 60. Or if you don't want to use parentheses, you can also just do 120 times 100 or times 1,000. Wait, did I do times 100 there? I did. Okay, I'll fix that in a minute. 120 times 1,000, and then just do divided by 1 divided by 60 and divided by 60 again. Yeah, 33.33. That's what I should have gotten up here, but I was off by a 0. Yeah, 33.33 meters per second. 33.33 meters per second after rounding. So let me go ahead and write that up here. Equals 33.33 meters per second. Once the conversion is done, you're good to go. It's pretty standard fare from here. So we have, what did they ask again? Calculate the minimum constant acceleration that the aircraft would require. So get acceleration first, and then part B, how long does it take? No surprise there, calculate the two missing variables. So for acceleration, I can use, if I have initial, final, and displacement, and I want acceleration, that looks like the third equation. V final squared equals V initial squared plus 2a delta x. Oh, and by the way, I should mention this. I will refer to them by their numbers. So when I say first equation, second equation, third equation, I do refer to them always in this order, first, second, and third. So remember which equation is which. The way I remember their order is just based on the number of squares in them. The first equation has no squares. The second equation has a square term. And the third equation has 2 square terms. So that's how I order them. So yes, I expect you to not be confused when I say first equation, second equation, third equation of kinematics. I expect you to not only know the equations, but also know their order, because that just makes it easier to communicate what we are doing when solving problems. So without further ado, let's go ahead and make our substitutions. We've got 33.33 squared equals, well, 0 squared plus 2 times, we don't know what the acceleration is yet, but we know the displacement is 240. 33.33 squared equals 2 times 240 is 480, so equals 480a. So if I divide both sides by 480, then 33.33 squared divided by 480 gives me 2.314. I'll round that to just 2.31. So acceleration needs to be about 2.31 meters per second squared. 2.31 meters per second squared, give or take. And of course, if the plane has more acceleration than this, that would be for the better. All right, part 2, how much time would it take? I'm just going to use the first equation so that I don't have to, well, actually, I don't have to do a quadratic if I use the second equation, so let's use it. Delta x equals v initial t plus 1/2 at squared. Since v initial is 0, it's not a quadratic anymore. Delta x, 240, is equal to 0 times t, so 0, plus 1/2 of 2.31 times t squared. Multiply by 2, divide by 2.31, so 480 divided by 2.31 is 207.792, and that's equal to t squared. If I take the square root, then I have plus or minus 14.41, it looks like. So t equals plus or minus 14.41. Minus 14.41 doesn't make any sense. Negative time doesn't really make sense here, did I? No, not meters, seconds. 14.41 seconds. And there we go. So the only real issue with that one was the conversion and also recognizing that the plane starts at rest. You are expected to have common knowledge like this. There's a book problem in the circular motion chapter of my book that doesn't give you any information. It asks you about the rotational velocity of the Earth around the sun. And rotational velocity is not in units of meters or anything like that. It can be in units of degrees or radians or rotations, and you're supposed to just know things about the Earth's rotation about the sun. One full rotation, or 360 degrees if you will, takes 365.25 days. That's how long 1 year is. So yeah, be on the lookout for problems where you are expected to use common sense and or common knowledge to fill in the information gaps. Okay, where to next? Let me take a sip of water first. All right. I highlighted, let's do this one next. It says a truck on a straight road starts from rest. Key phrase there, starts from rest, and accelerates at 2 meters per second squared until it reaches a speed of 20 meters per second. Then the truck travels for 20 seconds at constant speed until the brakes are applied, stopping the truck in a uniform manner in an additional 5 seconds. How long is the truck in motion, and what is the average velocity of the truck during the motion described? So this one, you don't actually have a constant acceleration. You've got 3 different accelerations, but you can split it up into 3 segments where each segment has a constant acceleration. So here I'm going to abandon initial and final as the subscripts of my V's, and instead I'm going to use numbers to keep everything straight. So phase 1 is going to have its first velocity as v0, second one is v1, its displacement is going to be delta x1, acceleration is a1, and time for the first phase is t1. Then I'm going to do the same thing for the next phase. The initial velocity of the second phase is the final velocity of the first phase. So phase 2 starts with v1 and ends with v2. Has a displacement we will call delta x2, has an acceleration we will call a2, and lasts for a duration that I will call t2. And then phase 3 will start where phase 2 ended, so it will start with v2, it will end with v3, it will occur over a displacement of delta x3 and have an acceleration of a3 for a time t3. Okay, let's fill in what we know. So reading the problem again, it says a truck on a straight road starts from rest, so velocity of the first phase starts at 0, and accelerates at 2 meters per second squared. The way trucks move, stepping on the gas will be in your forward or positive direction, so that's positive 2 meters per second squared, until it reaches a speed of 20 meters per second. So it ends with 20 meters per second, and now we know phase 2 starts at 20 meters per second as well. Then the truck travels for 20 seconds at constant speed, and because it's on a straight road, the direction is also constant, which means the velocity is constant in both magnitude and direction, which means the acceleration of the second phase is 0. And they said that this occurs for 20 seconds. Phase 2 occurs for 20 seconds. So it says, then the truck travels for 20 seconds at constant speed until the brakes are applied, stopping the truck in a uniform manner in an additional 5 seconds. So phase 3 starts with pressing the brakes until the truck comes to a stop. So V3 is 0. And they said that this occurs over 5 seconds. And did they give us anything else? They didn't tell us anything else, but they did say that the truck applies the brakes, and when you apply brakes on a truck, you slow down, which implies that the acceleration is opposite to the direction the truck is moving. So I would expect acceleration 3 to be negative, so I'm going to go ahead and write that negative sign in advance, just so I don't forget. All right, and the big questions are, how long is the truck in motion? So first question is T total. What is it? And question 2 is, what is the average velocity of the whole trip? Whole trip. Because the whole trip doesn't have the same acceleration throughout, it's going to have 3 different accelerations, we cannot use the conclusion from earlier where we just take the final and initial velocities. I mean, if you look at it, starts from rest and comes to a stop, there's no way the average velocity is going to be 0. That would imply that the total displacement has to be 0, and that definitely doesn't make sense for a truck that never turned backward, only moved forward and would either speed up, cruise, or slow down, but never change direction. No way that displacement is 0. Not if it moved in a straight line and in only one direction. Let's see, where do I want to start things off? Well, there's only one place to start things off, I guess. We've got 3 pieces of information for the first phase, so we can solve for the other 2. I mean, we don't really need the first acceleration to answer the questions, but we might need, well, we need to solve for it anyway because the acceleration is part of all 3 of our kinematics equations. So we can do, which equation do I want to use first? I guess I'm going to use my third equation here. V final squared equals V initial squared plus 2a delta x. I have it written there, so I don't have to write it again. 20 squared in this case would be the quote-unquote final velocity, equals 0 squared plus 2 times the acceleration times, wait a minute, I copied something wrong, didn't I? Oh, the acceleration is known, the displacement is unknown. My bad, my bad. This is the 2 meters per second squared, and this is unknown. I thought something felt off. Okay, so 2a and, well, I guess the a is actually 2, so I guess I'll write this as a delta x and write another 2 over there. That fixes it. Okay, so 4 delta x is equal to 400, which means 400 equals 4 delta x, which means that delta x is 100 meters. 100 meters. Okay, and let's go ahead and calculate t because we're going to need it for later. I will just use the first equation of kinematics since it's the easiest. First equation of kinematics is v final equals v initial plus at. V final, equals v initial plus at. V final here is 20 equals v initial is 0 plus acceleration is 2 times t. Divide both sides by 2. T is 10 seconds. Okay. Second phase, which I am now realizing we could have actually started with because we've got 3 pieces of information for it. If the acceleration is 0, then you could just use the first equation to conclude that the second velocity is the same as the first, or you could just common sense your way through it and say if it moves at constant speed, then its initial and final speed and every speed for that whole duration is going to be the same. Displacement, we have, it's actually just straightforward. If you use the second equation, delta x equals v initial times t plus 1/2 at squared. When the acceleration is 0, this just simplifies to delta x equals v times t, v being 20, so 20 times 20 seconds. So that's going to be 400 meters. So 400 meters there. And finally, phase 3. Well, since we know that V2 is 20, we can fill in one more variable here, and now we've got 3 values that we can use to calculate the other 2 for the third phase of this motion. I only need the displacement. Can I figure that out without knowing the acceleration? No. All 3 of my equations involve acceleration. I guess you could use that 4th equation, but I don't like depending on it too much. I think you can make do with just the first 3. So I'm drawing blanks. Hold on. Brain malfunction. To get A3, what would be the most convenient way given the 3 pieces of information we have? I guess first equation would be the best way to go about it. So V3, 0 equals V2, which is 20, plus acceleration 3, whatever it is, times T3 is 5 seconds. Subtract 20 on both sides, negative 20 equals 5A3. Divide by 5, A3 is equal to negative 4 meters per second squared. Okay, and now we can finally solve for delta x3. Delta x3 using, I guess, let's use the second equation. We could use the second or the third, but I feel like we've used the third quite a lot, so let's use the second for a change. So delta x3 equals v initial times t, so in this case v2 times t3, so 20 times 5, plus 1/2 the acceleration, so plus 1/2 of negative 4 times t squared times 5 squared. Okay, 20 times 5 is 100, And then 1/2 times -4 is -2, and 5 squared is 25. So -2 times 25 is -50 equals 50 meters. So delta x3 is 50 meters. Okay, and now we have everything we need to calculate the total time and the average velocity for the whole trip. The total time is just t1 plus t2 plus t3. T total equals t1 plus t2 plus t3 equals 10 plus 20 plus 5 equals 35 seconds. And then for the average velocity, we would need the total displacement, which is delta x1 plus delta x2 plus delta x3. Since they're all in a horizontal direction, I can just directly add them. I don't need to worry about Pythagorean theorem or anything like that. That's for 2 dimensions. If we're working in 1 dimension, simple addition and subtraction works. And then divided by the total time, which oh so conveniently is the first thing they asked us for. So divide by the 35 that we got earlier. Delta x1 plus 2 plus 3, we've got 100 plus 400 plus 50. So that's 550. I guess I'll write it down here. V average equals 550 meters over 35 seconds equals, let's see, 550 divided by 35 is about 15.71. About 15.71 meters per second. So if this truck had traveled at 15.71 meters per second for 35 seconds, it would have reached the same destination. Assuming, of course, there were no cars moving slower than it in the way, that would have resulted in a much more delayed arrival due to car accidents. I think it is time to look at a racing problem. Let me flip the lights on first because it's starting to get a little cloudy outside for me. I don't know how that affects the lighting that appears on screen. I need to check the exposure settings on this document camera. I'll have to remember to do that at some point. Watch me forget. Okay, yes, I do have a backside on this sheet, so let's work with that. Racing problems are common in kinematics, where you've got 2 things moving independently of each other and you want to compare their positions or their times or something like that. So we have, for our first racing problem, even if the 2 objects aren't in a race per se, I will still call them racing problems because they always tend to follow the same kind of strategy, whether it's an actual race or just 2 objects moving with no consciousness, no awareness, no intent to race with the other object. I will still call them racing objects anyway, or racing problems. 2 cars are traveling along a straight line in the same direction, the lead car at 25 meters per second and the other car at 30 meters per second. At the moment the cars are 40 meters apart, the lead driver applies the brakes, causing his car to have an acceleration of -2 meters per second squared. How long does it take for the lead car to stop And part B, assuming that the chasing car brakes at the same time as the lead car, what must be the chasing car's minimum negative acceleration so as not to hit the lead car? And part C, how long does it take for the chasing car to stop? Depending on your assumptions, you could actually mess this problem up really badly. So we'll analyze this a little bit more once we start solving, but let's go ahead and draw the situation. So we've got two cars. I'm just going to draw really blocky looking cars. So there's one car. I guess this will be the chasing car since it's behind. And then you're going to have the leading car, which is further ahead. And I will label that with an L for leading. And what information do we have on the two cars? So I'm going to keep two sets of information for these cars. I'm going to have V chasing initial and V chasing final, and delta X chasing and acceleration of the chasing car, and time of the chasing car, which in this case might not actually be the same as the time for the leading car. We will talk about that. For some racing problems, you would just use a shared timer or stopwatch, so to speak, for both objects, and sometimes you give them separate times and you have to just kind of think about the problem first in order to decide how you want to relate their times, if you're going to relate them at all. And then for the leading car, V leading initial, V leading final, delta X leading, acceleration leading, and time of the leading car. Let's list the information we have on both of them. So the lead car is at 25 meters per second while the other car is 30 meters per second. Lead car is at 25 meters per second. This is before they start braking. Chasing car is at 30 meters per second, so closing the gap. At the moment, the cars are 40 meters apart. When they are 40 meters apart, so when the front of the chasing car is 40 meters away from the back of the leading car. The lead driver applies the brakes, causing his car to have an acceleration of -2 meters per second squared. So acceleration of the leading car, -2 meters per second squared. How long does it take for the lead car to stop? If the lead car is going to stop, its final velocity is 0. Let's answer that question first before we reread the other parts of the problem. So we've got 3 pieces of information. We can get, I guess they asked for the time. We could calculate the displacement as well, which we're going to have to do anyway for the next part, but for now let's pretend that next part doesn't exist. So I'm going to do, let's see, initial, final, and acceleration and time. The first equation would work best for this. V final equals V initial plus acceleration times time. So I'm gonna do 0 equals 25 plus -2 times time, or you could have written minus 2t, which is something I will start doing eventually, but you know, the first few chapters of physics, it's usually fresh after summer break for a lot of students, so it might be worthwhile to slow down with my math a little bit and show some of these in-between steps. Just add 2t to both sides and divide by 2. 25 divided by 2 is 12.5 seconds. 12.5 seconds. And that's part A. Part B, assuming that the chasing car brakes at the same time as the lead car, which is not entirely realistic, but we would have had a more complicated problem otherwise. Usually, the chasing car has to have some sort of reaction time where it continues at its 30 meters per second for a little bit, for like a fraction of a second before it registers in their brain that the car in front of them is slowing down, and then they hit the brakes, in which case you would actually have to separate it into 2 phases, kind of like the previous problem we did. And you'd actually have to write 2 sets of information in that case. But yeah, they're simplifying for us. Assuming that the chasing car brakes at the same time as the lead car, what must be the chasing car's minimum negative acceleration so as not to hit the lead car? Not hitting the other object means not being in the same place as the other object at the same time as the other object. It means not being in the same place at the same time. So you need to know about position and time. Okay, well, for position, we need to add a little bit more to our drawing before we can piece together what's going on here. So the displacements of the 2 cars. Worst case scenario, how much space does the chasing car have to slow down? So the lead car is going to slow down and come to a stop at some point over here. Let's say, I'm going to say the back of the lead car moves from this location to, let's say it moves from here, not drawn to scale because I don't even know what this displacement is going to be yet. Maybe I would have known if I calculated delta XL. But yeah, this is delta XL over here. And the back of the leading car, I'm going to draw it dotted. The back of the leading car travels from here to here. And the front of the chasing car, worst case scenario, I would hope that it stops well before this distance, but worst case scenario, the chasing car, the front of the chasing car has all of this up until like a millimeter away from the back of the leading car. Delta X of the chasing car in the worst case scenario is this. And from our drawing, we can conclude that delta X of the chasing car, at best, or not at best, in the worst case scenario, delta X of the chasing car, well, not the worst case scenario, the second worst case scenario, because the true worst case scenario would be the cars colliding. So the second worst case scenario, stopping just a millimeter away from a car accident. Delta X chasing car would be equal to delta X of the leading car plus 40. 40 plus delta XL equals all of this. Okay. This relationship is going to help us because we don't have a lot of information here. Well, we do know that the chasing car needs to come to a stop, so I guess that's one piece of information we have. But we don't know how much time it stops in. It doesn't necessarily have to be 12.5 seconds. That is a common mistake that people will make. That does not have to be the case at all. In fact, that would be riskier because if you're trying to stop right behind the car that was initially moving slower than you and at the exact same moment that it stops, since you've got more initial velocity that you need to lose, you might need more time, even if you decelerate at the same rate as the car in front of you. In fact, you have to decelerate at a greater rate than the car in front of you in that scenario. So there's no real reason why the amount of time that the chasing car has to be equal to 12.5. In fact, it could be greater, and that's usually what happens if you think about how cars pile up at a traffic light. The car that's closest to the red light stops first, then the car behind it stops behind it a couple seconds later, then the car behind that one stops a couple seconds after that, and so on and so forth. They don't just all stop at the exact same time. So because we are missing our third piece of information over here, this will help us because it connects the information of the chasing car to the information of the leading car and might give us just what we need to make up for this lack of info. Let's see where I want to go with this. So if I go ahead and use my second equation of kinematics, can I do anything with that? Actually, before I do that, I can calculate delta XL. Yeah, that's what I should be doing first. I knew I was forgetting something. Yeah, let's go ahead and calculate delta XL so that we have an actual number here. So if I guess I could use the second or the third equation here. What would be better? I guess I'll use the third equation. V final squared equals V initial squared plus 2a delta x. So we've got 0 squared equals 25 squared plus 2 times negative 2 for the acceleration of the lead car times delta x of the lead car. 25 squared is 625. 2 times negative 2 is negative 4. Negative 4 delta XL. If I add 4 delta XL to both sides, I get this. And divide by 4. 625 over 4, I think, is going to be 125. No, hold on. No, I don't think so. 625 over 4 is 156.25. A little bit more. So I get delta XL 156.25 meters. Okay, and that tells me that delta X for the chasing car in the second worst scenario is 156.25 plus 40. So delta X of the chasing car, second worst scenario, 156.25 plus 40 equals 196.25 meters. 196.25 meters. that in for here. And now we can calculate what they asked us for, which was the acceleration needed. So I would use, I guess, third equation again. If I'm solving for acceleration, let me switch colors. How about red? So I'm going to do v final squared, which is 0 squared, equals v initial squared, which is 30 squared for the chasing car, plus 2 times acceleration times displacement, 196.25. Did I get all that? V final, V initial, 2 acceleration and displacement. Yep. I'm going to subtract the 30 squared on both sides, so I get negative 900 equals whatever that is. 2 times 196.25 is 392.5 equals 392.5 times acceleration of the chasing car. And if I divide negative 900 by that 392.5, I get negative 2.29. I get the acceleration needs to be negative 2.29 meters per second squared, or less. I would feel more comfortable if it was something like negative 2.5 instead. Was there anything else to this problem? So that was part B. How long does it take for the chasing car to stop? How long does it take for the chasing car to stop? So now that we know this, we should be able to solve for TC pretty easily. We can use first equation would be the easiest. Second equation I don't recommend unless you're in the mood to use the quadratic formula when you don't need to. There will come a time where we absolutely can't avoid it, but today is not that day. So first equation it is v final equals v initial plus at. 0 equals 30 plus negative 2.29 TC. If I add 2.29 TC to both sides and then divide both sides by 2.29, I get 30 over 2.29 is about 13.10. TC is about 13.10 seconds. And I'm not surprised at all that it is longer than the 12.5 seconds because of what we discussed a couple minutes ago. That's just how cars stop behind each other. The front car stops first, then the second car rolls in a little bit later, then the third car rolls in a little bit after that, and so on and so forth. That is more realistic. Now, if I really wanted to analyze this problem even further, I would actually use these two accelerations and check to make sure, just to be extra sure, that there is no time where both cars are at the same position at the same time before 12.5 seconds, but that's kind of overkill. It is something that, well, let me think. Would we actually need to check it given our current assumptions? Let me see. So negative 2.29. If we decelerate at negative 2.29 meters per second squared and we start off with a 30 meter per second advantage, or sorry, if we start off with a 5 meter per second advantage over the leading car, then it would only take like 2-ish seconds 2 seconds and some change. So to lose that first 5 meters per second, I might be overthinking things here, but I feel like this might be worth exploring on from a conceptual standpoint. Let's see. So they already have a good amount of distance between them to start with. If they had both continued moving without hitting the brakes, then it would have taken 8 seconds for the chasing car to catch up to the leading car. That's without deceleration. Having deceleration extends that time. Would it extend that time by at least 4.5 seconds? Is there I'm trying to look for some sort of intuitive reason why we wouldn't have to actually do the math that I'm thinking of to check that the two cars are never at the same position at the same time during this whole deceleration thing. I think that's something I'll just have to think about and reflect on my own time after the stream. I think it's in our best interests to just move on from this for now. I think I will save that problem for next time. Same thing for that problem. How long have we been going? Well, we have been going about 3 hours, so what I think I'm going to do is grab a couple of problems from the OpenStax book, like 2 or 3 of those, and then we can call it a day for the physics lesson. And then next week we will do a couple more of these horizontal motion problems and start introducing free fall. Okay, let's switch over to our textbook problems and see what chapter were they in again. Let me check the course plan. They were in chapter 2. Okay, chapter 2. Let's go to problems and exercises. And we were looking at starting from 1 through 7, 11, 13, and so on. Let's read through them and see what we've got. We already talked about displacement and time, velocity, and speed. Yeah, let's skip over to the acceleration section. Especially over here, 2.5 motion equations for constant acceleration in 1 dimension. So we have, does 20 look interesting? Does it look different from anything we've done so far? Olympic class sprinter starts a race with an acceleration of 4.5. Yeah, that's standard. Nothing we need to worry about. We've already done enough that should be easy for you guys. A well-thrown ball is caught in a well-padded mitt. If the deceleration of the ball is that much, now we're good with that. Bullet in a gun, I don't think so. Did I star any of the problems here? I starred 55, but I think 55 is after the free fall section, so I don't want to look at that yet, since it might involve topics we haven't discussed yet. These are all fairly standard so far, based on, like, me skimming them. No, that's also pretty standard. Anything involving either multiple phases of motion or racing would be good. No, no good there. Oh, we might have something here. Dragsters can actually reach a top speed of 145 meters per second in only 4.45 seconds. Considerably less time than given in previous examples earlier in the textbook. Calculate the average acceleration, blah, 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 blah. Does not involve racing between two objects, so that's a no. Oh my goodness. Did I overestimate the qualities of these exercises? I mean, it's nice to have a lot of standard problems, but give us something a little bit more advanced. I might actually have to look further down for those. I think that's the way they structure this book. They start with mostly standard problems and then they put the really advanced problems towards the end of the list. That might be what's going on here. I've seen textbooks that do it this way. Just goes to show how much I remember from whenever it was that I went through this and listed my recommended list of problems. Just one racer there. Wow, we went through that whole section, the whole 2.5 section, and nothing. Okay, let's look and see if there's any... No, there's... Okay, well, then I think I should just continue picking problems from my book. Yeah, I think I should just continue picking problems from my actual physical textbook instead. If this is the quality of the problems we're getting, then I'm actually going to press on. Let me grab... I shouldn't have closed it. Now I have to find the page again. Let's see. And did I switch back to the camera? Yes, I did. Okay. Definitely don't want to make that mistake again. Okay, let me find another racing problem. Actually, you know what? Let's downgrade a little bit and go back to some problems where there is no acceleration. Let's go back to a non-acceleration problem that I forgot to cover before. That might be worthwhile. So let's do... Where did it go? I know I have it here somewhere. Ah, yes. So it says a tortoise can run with a speed of 0.1 meters per second, and a hare can run 20 times as fast. In a race, they both start at the same time, but the hare stops to rest for 2 minutes. The tortoise wins by a shell, which is apparently 20 centimeters. Part A, how long does the race take? And Part B, what is the length of the race? There is no acceleration to be mentioned here. So it says a tortoise can run with a speed of 0.1 meters per second. So we're talking about constant speeds here. Speed tortoise, I'll just call it S tort, equals 0.1 meters per second. And a hare can run 20 times as fast. So speed of hare, 20 times 0.1 is 2 meters per second. And it says in a race they both start at the same time, but the hare stops to rest for 2 minutes. The hare stops to rest for 2 minutes. The tortoise wins by a shell. So I guess I want to draw 2 race tracks here, one for the tortoise and one for the hare. This is what I will usually do for racing problems. I'll draw 2 tracks, one for each object, or 3 if there happens to be a third object, but that's incredibly rare. Should they be the same distance? No. I should have cut this off like over here. Yeah, and then scribble that out. Okay, so the tortoise travels the entire race. This is the tortoise. Travels the entire race, while the hare travels the entire race except for the little bit by which the tortoise wins. So they said the tortoise wins by a shell, which is the equivalent of, they said 20 centimeters. Or if I convert it, 20 centimeters is equal to 0.2 meters. 20 hundredths of a meter is 2/10ths of a meter. So yeah, 2 separate tracks. For the other racing problem, I drew them on the same track because, well, the problem itself had them physically on the same track. Right, the chasing car was not in a position to pass the leading car. It would have just collided with the leading car if it reached the same horizontal position. But usually this is what I will do. I will draw separate tracks for separate objects. So the amount of time that is spent on the race. For the tortoise, we've got let's see. So I want to separate 3 things. So we've got the time of the race is how long the race lasts, which is equal to the time of the tortoise, how long the tortoise is in motion. The time of the hare does not equal the time of the race, because I'm defining the time of the hare as the amount of time that the hare is actually moving. And the race is the amount of time the hare is moving plus the amount of time that the hare is resting. So T race, the time that it took for the race to be completed, is also equal to the time that the hare is actually in motion plus the 2 minutes that the hare is not in motion. I'm going to convert that to seconds. 2 minutes is 120 seconds. So I guess I can just put these 2 equations together and say time of the tortoise equals time of the hare plus 120 seconds. Okay, so that's one piece of information we need. And then the other equation that we need in order to finally solve this, so let me actually put this all together in one equation. Motion time of the tortoise equals motion time of the hare plus 120. And then there's a relationship between their displacements, or I guess in this case distances, since they referred to speed, but you could still use displacement here if it's just a straight line race. So we can say that the displacement of the tortoise, this whole pink line, or distance tortoise, I keep on saying displacement out of habit, d tortoise, is equal to I'm going to define the distance of the hare as the distance that the hare actually traveled, not the distance of the race. So d hare, the distance that the hare traveled, plus the distance that the hare failed to travel by the time the race ended, which is 0.2 meters, that little blue part over there. Okay, this should be easy from here. We can define the distance as distance tortoise equals the speed of the tortoise times the time during which the tortoise is moving, and distance traveled by the hare, before the race is over at least, is equal to the speed of the hare times the time that the hare was actually moving. So not including the 120 seconds of rest. Okay, now I can just make these substitutions right here. And if I do that, then I get speed of tortoise 0.1 times t tortoise, so 0.1 times t tortoise equals speed of the hare is 2 meters per second times time of the hare is, well, we don't know yet. So we've got 2 times t hare plus 0.2. Okay, so we now have one equation, two equations in the same two unknowns, which means we should be able to solve as long as the equations are independent, and there is no reason why these equations are not, there's no reason to conclude that these two equations are not independent. I mean, we arrived at them in different ways. We didn't use either one to get the other, so we should be good to go here. I will replace, I guess, what was the question asking? It was asking how long does the race take and what is the length of the race in terms of, distance. So how long the race takes, that would be t tortoise. But I do feel tempted to just use t tortoise and substitute it in here instead, and then calculate it later by plugging t hare back into this. Yeah, I think that's what I'm going to do. So plug in t hare plus 120 for t tortoise over there. I guess I'll do it right here in this empty space. I might potentially be able to spare an extra page of paper here. 0.1 times t tortoise is t hare plus 120 equals 2 t hare plus 0.2. Instead of distributing the 0.1, I'm just going to multiply everything by 10. That gets rid of the 0.1, and I'm left with t hare plus 120 equals 20 t hare plus 2. Subtract t hare from both sides and subtract 2 from both sides, and I get 19 t hare is equal to 118. 118 divided by 19 is 6.21 seconds. So I guess, let me switch colors and write it over here. T hare is equal to about 6.21 seconds. That means t tortoise, which is also t race, is equal to 6.21 plus 120, so 126.21 seconds. All right, that's our first answer, and then our second answer is how long in terms of distance is the race? We could either plug in 6.21 over here and get 2 times 6.21 plus 0.2, or the easier way is probably to just calculate the distance traveled by the tortoise, since the tortoise traveled the entire race. So tortoise is 0.1 meters per second multiplied by the time of the whole race is 126.21, so d race is equal to d tortoise is equal to 12.621 meters. And there you go. That's another racing problem that doesn't involve acceleration. I probably should have covered that one last time, but it slipped my mind. Then we've got that hockey player problem and the cable car problem. I think I will just kind of introduce. I will read out the cable car problem and we will solve it next time. But the hockey player problem, I think we can cover real quick and then we will wrap up with that. So we have, which color have I not used much? I guess this one can have a go. Actually, I don't think I've used navy blue in a while. So it says a hockey player is standing on his skates on a frozen pond when an opposing player, moving with a uniform speed of 12 meters per second, skates by with the puck. After 3 seconds, the first player makes up his mind to chase his opponent. If he accelerates uniformly at 4 meters per second squared, then A, how long does it take him to catch his opponent? And B, how far has he traveled in that time? And it also says assume that the player with the puck remains in motion at constant speed. And if we assume that they move in a constant direction, then that would then allow us to set their acceleration to 0. So a hockey player is standing on his skates on a frozen pond. I'm going to draw 2 separate tracks here. Track 1. Hold on, let me read the problem again before I start drawing these tracks because I feel like I might screw something up here. A hockey player is standing on his skates on a frozen pond when an opposing player moving with a uniform speed of 12 meters per second skates by with the puck. After 3 seconds, the first player makes up his mind to chase his opponent. If he accelerates uniformly at 4 meters per second. Okay, or 4 meters per second squared. Okay, so there's going to be, I guess, I'll draw the player that passes by first. For some amount of time, they're traveling before the person starts chasing them, and then the other hockey player starts chasing them. Again, I don't know how these are going to scale. It could very well be the case that this second displacement is smaller than this one. We don't have enough information to make that call, so if the proportions are off, that is why. So we've got Would this be our first hockey player or our second? Why is my brain malfunctioning right now? I've done this problem so many times before, too. This would be our guy passing by with the puck. So they are going to actually start over here while our chasing player starts over here and is supposed to catch up to them at some point. Okay, so this person passes by this person, comes here, travels all the way to here, and then this person finally makes up their mind to start chasing. That's the situation we're working with. So we've got 3 seconds. 3 seconds it takes until this guy gets to travel for 3 seconds before this other guy starts chasing him. And this person is moving at a constant 12 meters per second. 12 meters per second. This person, on the other hand, is starting from rest. So this person, V initial, is 0. But they also have an acceleration, and the acceleration is 4 meters per second squared. Acceleration is 4 meters per second squared. And that is all the information we have. I guess I can go ahead and write that this person's acceleration is 0. How long does it take him to catch his opponent, and how far has he traveled in that time? Okay, so there are 2 different ways, there are 2 different perspectives on how you want to define time for this situation. You could either use a single stopwatch, so to speak, starting from the moment that this person finally decides to start moving. Or you could have a stopwatch associated with this person's motion time and another stopwatch associated with this person's motion time starting from when they were back here. If you think about timing these people using stopwatches, that's kind of what I'm referring to. Think of it as a question of how many stopwatches are you using, or are you just using a single stopwatch to time everybody? Sometimes it makes more sense to just have separate stopwatches for each person, and other times it makes more sense to just have a single stopwatch. And sometimes you can do both and make it work. In this case, I would rather just have a single timer that starts when this person is right here and when this person has started moving. So my stopwatch starts when the actual chase starts. So these first 3 seconds would not be recorded then. You could also do the other way, where you record the amount of time that this person is in motion separately from the amount of time that this person is in motion, and then you could say their timers differ by exactly 3 seconds. So yeah, it's completely up to you. Over time, once you practice enough of these problems, you'll find your own preference. Or you might discover that one way of doing it is easier than the other. But what I'm comfortable with for this particular problem is just a single timer for both of them. And instead of having to add 3 seconds to the timer of one of them versus the other, what I want to add instead is whatever this displacement is, whatever this, I guess I'll call it delta x0 is. I would rather just add that and write an equation that relates their displacements to each other. And I can actually calculate this delta x0 off the bat, because if they have a constant velocity, then I can just do 12 times those initial 3 seconds. This must be 36 meters. So they start with a 36 meter lead. And then I'll call this delta x of the leading player, and I'll call this delta x of the chasing player, and I will write the relationship delta x achieved by the chasing player, assuming they catch the leading player, is delta x of the leading player plus 36. And then time of the chasing player equals time of the leading player, which I will simply refer to as t. This is assuming I start the timer when this guy is over here. This equation, both of these equations actually could be different depending on how you want to assign your stopwatch or stopwatches. I guess I'll go ahead and write down the other version that you could do is you could say these delta x's are the same. You could say delta x chaser equals delta x leader equals delta x, and you could say t chaser plus 3 equals t leader. So that's the alternative solution. We're not going to do that here, but that's what it would look like. Okay. So we've got that. Let's copy down the other values we know in a more organized fashion. So we have v initial is 0, v final unknown, acceleration 4, displacement is just delta x chaser, whatever that is, and time is just whatever that t is for both of them. Okay. This isn't actually a known value, but what we can do is we can take advantage of this. I can substitute both of these delta x's using the first equation of kinematics. I can do, or not the first, the second. The second equation of kinematics is delta x equals v initial times t plus 1/2 a t squared. I can do delta x of the chaser is, well, 0 times t plus 1/2 of 4 times t squared. So 1/2 of 4 times t squared, that's delta x chaser, equals delta x of the leader is going to be 12 times the same amount of time measured from this point. Remember, the 3 seconds are already accounted for in our version of the solution. So 12 times t plus 1/2 of their acceleration times time squared. Well, their acceleration is 0, so plus nothing. And then they've got the plus 36. So delta x of the chaser plus equals delta x of the leader plus 36. And this we can solve. So this is going to be 2t squared, and then I'm going to subtract 12t, and I'm going to subtract 36. And that equals 0. This is one of those unavoidable quadratics that I was talking about. I can factor out a 2. if I divide everything by 2, I get t squared minus 6t minus 18 equals 0 divided by 2 is 0. And is this factorable? Let me see. 3 and 6, no. 2 and 9, no. Yeah, we're going to have to use the quadratic formula for this one. All right. So negative b, that's negative 6 or positive 6, plus or minus the square root of negative 6 squared is the same as positive 6 squared is 36, minus 4 times 1 times negative 18, which should be plus 72 if I'm not mistaken, all over 2a, so all over 2 times 1, so all over 2. Let's see, 4 and 18 is the same as 8 times 9. Yeah, 72. So 36 plus 72 is 108, the square root of which I don't know, so off to the calculator. I guess I might as well show how I do this on the calculator. So first of all, fraction button is your friend if you have it on your calculators, and if you don't, you might want to get at least this type of calculator or a higher grade. This, I think, back when I bought it, it was $30. Who knows how much it's worth now. But should be relatively cheap if you don't want to buy a full-on graphing calculator. Though you might want to buy a graphing calculator anyway if you plan on taking calculus. 6, I'm going to do plus, and then square root 108. I guess I'll do, yeah, I'm confident about the 108, so I don't need to check my math on that. All over 2. Okay, I think what I want to do to make sure that it doesn't write it in that form is I'm going to write 0.0, and that usually tells the calculator to convert it to a decimal. Yeah, there we go. So that's one potential answer. And then copy it and edit the plus into a minus. And there's your other possible answer. So t is either 8.196, which I would round to 8.20. Actually, you know what? I'll round it to 3 decimals, 8.196, or negative 2.196, which doesn't really make sense in this context. Negative time would mean, I mean, it does kind of make sense if you actually plug it in. If you actually plug it in, then it would give you the amount of time where if everybody started moving backwards in time, so if you changed this person's acceleration to -4 and you changed this person's velocity to -12, it would give you the amount of time it takes for them to catch up to each other by going in the opposite direction in time. Hold on, I might be mixing up which values actually switch signs, but if you were to plug in negative 2.196 into your other equations, you'd find that it's the equivalent of what if they were just moving backwards instead of forwards. That's what the negative would give you, but of course that's not our situation. These people are moving forward in time, not backwards. So 8.196, the only positive result. T equals 8.196 seconds. That's for both of them. So this is both of them having moved for 8.196 seconds since the lead player arrived at this location. That's the amount of time it would take for this chasing player to get here and catch up to them. And the second part of the question is asking how far did was it the chaser or the leader? Let me read again. How far has he traveled in that time? He is the guy who accelerates, so the chasing player. Okay, so what is delta x of the chasing player? Now that we have t, we can just plug into the second equation of kinematics. Delta x of the chaser, we already said earlier, there's 0 initial velocity, so 0t plus 1/2 of 4 times t squared times 8.196 squared, and I should write the 8.196 over there, come to think of it, and box that as one of my answers. And calculator for this, so 2 times 8.196 squared. I'm getting 134.35 almost. 134.35 meters is how far they traveled, and if they were to ask how far did the other player travel, just subtract 36 from that, and you're good to go. And I think this is where I will end the lesson for now. Oh, actually, wait, no, before I end things, let's read the next problem so you can at least spend some time thinking about it over the week. We have, this problem says, a certain cable car in San Francisco can stop in 10 seconds. So we've got a certain cable car in San Francisco can stop in 10 seconds when traveling at maximum speed. It doesn't tell you what that maximum speed is. On one occasion, the driver sees a dog a distance d meters in front of the car and slams on the brakes instantly. The car reaches the dog 8 seconds later, and the dog jumps off the track just in time. If the car travels 4 meters beyond the position of the dog before coming to a stop, how far was the car from the dog? And then there's a hint that says you will need 3 equations. This one can be quite tough in figuring out which 3 equations you need to put together. This one sounds simple, but getting the right equations can be a bit of a headache. So let me draw the situation. So they've got a cable car traveling at Vmax. I'm just going to draw some sort of square. It's traveling at some maximum speed I will call Vmax. And there is a dog that is d meters away. There's a dog that is d meters away from the cable car. And the cable car slams the brakes and comes to a stop 4 meters after the location where the dog was standing on the tracks. And we know the amount of time it takes to come to a stop. Starting from maximum speed, we know the amount of time it takes to come to a stop is 10 seconds. We know the amount of time it takes to come to a stop is 10 seconds, and we know that the time it took to reach the dog and narrowly avoid a collision with it was 8 seconds. So that's all the information that we are given, and based off of that, you are expected to calculate the value of d, assuming, of course, that the deceleration of the cable car is constant. You would expect it, of course, to have a negative value since you're slowing down from some rightward velocity to 0. Oh, and I guess I should write that in the diagram too. At this point, v final equals 0. So yeah, that is the problem. It can be quite tricky, especially for students that are learning kinematics for the first time. So have a look at that. We will solve it next time. And I will address that other problem that I got stuck on. Well, not problem, but proof that I got stuck on with the negative acceleration thing. I'll think about that and see if I can come up with a cleaner way to prove that our equations of kinematics still work if our graph was sloped down rather than up. And I will also be doing free fall next time. We will talk about things that accelerate due to the influence of gravity. We will talk about vertical kinematics, basically. And then we will just do a bunch of problems involving free fall, and probably continue doing problems for the week after that before transitioning to the topic of projectile motion. It all depends on how far we get next week. But yeah, that's the plan. Next week is wrapping up the horizontal kinematics and transitioning to vertical kinematics and seeing how far we get with it. If you want to stick around, what I plan on doing after this is covering a little bit of calculus. So yeah, I'm going to take like a 15-minute break and then I will be back for that. Anyway, for those of you who are only here for the physics, class dismissed. For those who are interested in the little bit of calculus I want to do, I want to introduce some concepts involving Riemann sums. You are more than welcome to stick around. I will be back in 15 minutes. Take care, and I'll see you then.